This is part B for our unit on multiple contrasts. And I have here just a random picture from the 1960s, I believe, that I then tried to Photoshop. But anyway, so our unit is looking at situations where we want to make comparisons between more than two groups. Maybe we have 3, 4, 5, or 6 different groups, and we want to see if there's a difference between groups on levels of some outcome variable. And in the previous section, we looked at how we would address the omnibus question. That is, if we have a question, overall, is there a difference between groups? And we would address that omnibus question. The effect size would be eta squared, would tell us the percent of variance explained, that is, the percent of variance in the outcome variable that's explained by group membership. And then we would test the significance of eta squared with an F statistic. We would do an analysis of variance and calculate F, and that would test the significance of eta squared. Now, I want to talk about focused questions, where we're making comparisons between just two things that we can hold in two hands. And first, I want to talk about something called planned contrasts. And this will be part 2. And then the next part, which we could call part 3, we'll talk about doing post hoc contrasts. So first, let's talk about planned contrasts. So to explain the idea of making planned comparisons, the first thing to do is to talk about something called coding. And coding is something that we've actually been doing all along. I just haven't given you a term for it. So recall back to the unit when we talked about simple contrasts, when we were making comparisons between just two groups. Maybe we had a treatment group and a control group. And recall how we used group membership to create an X variable or a predictor variable. And we assigned people values on this X variable depending on what group they were in. Maybe they got a value of 1 if they were in the treatment group, and they got a value of 0 if they were in the control group. So we created a predictive variable or an X variable and gave people values on that predictive variable that were determined by what group they were in. And we've done that before, and now I'm just telling you, when we do that, I'm going to call that coding. Coding is when we create an X variable and people have scores on that X variable that are determined by group membership. Say, for example, I was wanting to test a treatment for that statectomy sadness, that sadness that people experience when they near the end of their statistics classes. And so maybe I have this treatment, which I call this, green gas, maybe this green happy gas aromatherapy. And that's my treatment. And maybe if I expose people to this green happy gas, they might feel happier and not so sad about the end of their statistics class. And then maybe I have a control group, which I just expose these people to this inert object and they sit around or watch the stapler, which is not supposed to have any effect. So I have my happy green gas aromatherapy treatment group and my control group. And I get a sample of people that maybe they've finished their statistics course and they're feeling sad because of the loss of statistics and they're experiencing some statectomy sadness. And I randomly assign this sample of people. Some of them get randomly assigned to my happy green gas aromatherapy, and some of them get randomly assigned to the treatment group. And then just to go back and review from the things we were talking in that previous unit on simple contrast, if I have two groups, my X variable is going to be a group membership variable. And I'll say if you're in the treatment group, your score on X will be 1. And if you're in the control group, your score on X will be 0. And X will be the group membership variable. And then the Y will be the outcome variable. So Y could be maybe your level of happiness at the end of treatment. So in this case, we got two groups, and we have an X variable and a Y variable. The X variable is group membership, which is scored either a 0 or a 1, depending on what group you're in. And Y is the outcome. It's a numerically scaled outcome that ranges from high to low, which in this case maybe is levels of happiness. And this is just a review of what we've done before, but I'm clarifying that this process of assigning numbers to people based on what group they're in, creating this X variable that's either a 0 or 1, that process is called coding. Now, what I want to do is take this example and show you that we've actually been talking about the same thing throughout several units. So this sounds like what we were talking about in that unit on simple contrasts. And then we also had a unit where we talked about correlation, we talked about regression, and then this unit we've been talking about doing analysis of variance for group comparisons. And it might seem like these are all different things, but they're actually not. We've actually been talking about the same thing over and over and over again. It's just different language, different little twists of the exact same thing. So what I want to do now, before I go on and explain exactly what planned contrasts are, is to show you how we've been talking about the same thing all along. Specifically, what I want to do is look at the equations that we used back in that unit when we talked about simple contrasts, and look at the equations we used to analyze this type of study, and then see what would happen if we used the equations that we talked about in later units, and show you that actually all these equations are different versions of the same thing. So if we go back to that unit on simple contrasts, if we have two groups, our treatment group gets that happy green gas aromatherapy, our control group gets nothing, they just watch a red stapler, and we have this x variable, which is assigned a value of 1 if you're in the treatment group, assigned a value of 0 if you're in the control group, and the outcome variable is variable y, which is levels of happiness. And recall the basic linear equation that I gave you for analyzing data in this type of study. We talked about how we'd have at y hat, predicted y, which is a person's predicted level of happiness. And we had this equation where we said the predicted level of happiness was equal to a mean for group 0, the mean for the control group, plus a difference between the two groups, the mean for group 1 minus the mean for group 0. That's the difference between groups in their means, or another way of saying the same thing. It's the expected increase in happiness if you go from group 0 to group 1. If you go from the control group to the treatment group, it's how much you expect happiness to go up. And then we multiply that times a person's score on x. And again, x is either a 1 or a 0, depending on what group you're in. So that was the equation that we were using back in our unit on simple contrast to analyze data in this type of study when I have two groups and I want to see if there's a difference between these two groups in levels of an outcome variable such as happiness. So at the bottom of this slide I have the equation that we were just looking at, the equation from that unit on doing simple contrasts, when I'm just comparing two groups to see if there's a difference between two groups in their mean levels of some outcome variable. So the bottom equation is from that unit doing simple contrasts, and then at the top here I have the equation from the unit that came after that, which was our unit on regression. And we talked about simple regression. And so let's look at that equation for a simple regression equation where we say predicted y hat, is equal to an intercept plus a slope times someone's score on x. So that was the equation we looked at in simple regression. And now the thing I want to show you is that these are actually the exact same equation. It might have seemed like they were different, but these are actually the same equation. Because when we do regression, we say predicted y is equal to an intercept. Well, what is an intercept? Your intercept is your expected y when x equals 0. That's what an intercept tells you. Well, if you've scored things so that we have x is a group membership variable scored as 0s and 1s, so that 1 is your treatment group and 0 is your control group, then when x equals 0 is the same thing as saying if you're in group 0, if you're in the control group. And so the expected y when x equals 0 and is simply the mean for group 0. That is, recall that if we have group membership, what is someone's predicted score on y? Well, their predicted score is simply the mean of whatever group they're in. We talked about that in the previous video. So if someone's predicted score is simply the mean for whatever group they're in, if they're in group 0, then the expected y when x equals 0 is simply the mean for group 0. So our intercept right here, beta naught, is the same thing as this mean for group 0 I have down here in the bottom equation. It's the same thing. I gave them different labels, but mathematically it's the same thing. It's the mean for group 0. It's the expected y when x equals 0. It's the expected y when someone's in group 0. Then So in our regression equation, then we take, we have our y hat is equal to our intercept plus our slope times x, and our slope is the expected increase in y given a 1 unit increase in x. So if we recall from our unit on regression, that's how we defined a slope, the expected increase in y given a 1 unit increase in x. And that is the exact same thing as what we have down here in the bottom equation. It's the difference in means between our two groups. The mean for group 1 minus the mean for group 0 is the difference between groups. That is the expected increase for group 1. That is, if you go from group 0 to group 1, how much do you expect y to go up? It's the difference between groups. And so right here, that's what we have. The expected increase in y given a 1 unit increase in x is the difference between groups. It's the expected increase for group 1. So again, it's the same thing. So in our regression equation, our intercept is the same thing as the mean for group 0. Our slope is the same thing as the difference between two groups. And in both cases, we have an equation that takes, if I can click on my clicker there, it's not letting me click where I want to click for some reason. There we go. So in both equations, we have the intercept, or the mean for group 0, plus the difference between groups, that is our slope, times a person's score on x, which is group membership. So in those two units, we were actually talking about the exact same equation. And also recall from our unit on simple contrasts that we talked about effect sizes. And usually, if I'm comparing two groups to see if they differ from each other on some outcome variable, the usual effect size to report would be a D statistic. But we could also calculate a correlation, and we talked about that previously. And the correlation, we can think of this a couple different ways. We can note that the correlation is simply the correlation between x, which is group membership scored as 0s and 1s, and y, which is the outcome variable. For example, in this case would be levels of happiness. And so everyone has a score on x. In this case, it's going to be 0s or 1s, depending on what group you're in. Everyone has a score on y, which is the level of happiness. And we can calculate the covariance between x and y and divide that by the product of the two standard deviations. And we have our correlation between x and y. And that is a measure of effect size. Now, a D statistic would be a more common way of giving an effect size for the situation where I'm looking at a difference between two groups. But the correlation would also be a measure of effect size. And if you recall from our unit, when we talked about simple contrasts, I gave you this formula here that we could use. And this is a formula that we've seen other places too, that anytime we do an analysis and we calculate a t-value, if we do an inferential statistic, and the inferential statistic is a t-test, and we get our t-value, we can take this formula where we take t squared divided by t squared plus degrees of freedom, then we take the square root, and that will actually calculate a correlation. So it's kind of a shortcut formula that will give us the value for a correlation. So we can get the same correlation this way. We can get the correlation by calculating the covariance between x and y, dividing that by the product of two standard deviations. That will give us a correlation. Or if we've done a t-test, we can take our t squared divided by t squared plus degrees of freedom, take the square root, and that will give us the exact same correlation. I also noted before that we can call this correlation a point by serial correlation. And over here, I just say R with no subscript. This one I have RPB, but that's just random. We could have put PB over here too. If I wanted to, we could put PB there because these are both, if I'm looking at the correlation between X and Y, and if X is dichotomous, meaning they're just two groups, then we can call our correlation a point by serial correlation. This is just a fancy term we can use whenever our X variable consists of just two groups. We can call our correlation point by serial. So here I put the term PB for point by serial on the right, but on the left, I didn't have that on my output, but either way would be correct. Now, let's take this one step further and think about our unit on regression. So if we take X and predict Y in a regression equation, where we say predicted Y is equal to an intercept plus a slope times X. And if we turn everything to z-scores prior to analysis, then we will get our standardized beta, And recall from our unit on simple regression that if I have just one predictor, and I turn everything to z-scores prior to analysis with just one predictor in simple regression. This wasn't true for multiple regression. This changes if we have more than one predictor. But if I have just one predictor in my simple regression equation, then my standardized beta is the same thing as my correlation, because the formula for the standardized beta was simply the covariance of x divided by the variance, SD squared, of x, rather than the product. And if everything is turned to z-scores, then standard deviation of x is going to be 1, variance of x will be 1, product of two standard deviations will be 1, these will all be 1, so that would mean that your formula for your slope and for your correlation are all the same thing, and that's just reviewing from what we talked about in our previous unit on simple regression. So if I have just one predictor, then my standardized beta is the same thing as my correlation, and I could calculate the correlation using this formula here, using my t-test, or I can use the standard formula for calculating a correlation. These are all different ways that will give me the exact same value. So this is showing you another way that many things we've been talking about through the semester are different ways that will actually give us the exact same information, just slightly different versions of the same thing. Then in our previous video, we were looking at how we can calculate an F statistic. We can do an analysis of variance and calculate an F statistic, which is an inferential statistic that will test the significance of our omnibus effect when we're doing comparisons between more than two groups. Let's think about this ANOVA and this F statistic if you had just two groups, and how this would look and how we would get the same thing whether we're approaching this F statistic from a regression approach or from a group comparison approach. So we could think about, if I have just two groups, we could take a regression approach where we say predicted y, say predicted happiness, is equal to an intercept plus a slope times x, where x is just group membership, scored say zeros and ones depending on what group someone's in. And we saw just a moment ago how when we do this, our intercept is going to be the mean for group 0, and our slope will be the difference between two groups. That is, if we've coded our groups, scored our groups so that one group, so our treatment group is group 1 and our control group is group 0, then all this works out just right. And so we could use that and calculate, do our regression. Here's our regression equation. And from this equation, we could calculate what is our sum of squared explained variance, what is our error variance, and what our total variance. And we could calculate that and do our F statistic, thinking of it from a regression approach. Or we could do what we did in just the previous video that was more of a group comparison, where we were looking at the error was how far people deviated from their group means, which again, as we're seeing up here, is true that how far people deviate from their group means is the same thing as how far they deviate from their predicted values. And now what we see is actually, if you do a regression equation, it will actually give you predicted values. At least at this point, we're just looking at if I have just two groups. But we're seeing how your predicted value actually will be your group mean. So how far you deviate from your group mean is actually the same thing as how far you deviate from your predicted values. So if we're thinking about it from the group comparisons approach, we call our error variance, we call that within group variance because it's how far people deviate from the group means. We call the explained variance the between groups variance because that's how far the group means deviate from the grand mean. But either way, if we do like what we were doing in the previous unit where we were doing a group comparison approach and calculate our total, error, and explained variance sums of squares, we would get the exact same values that we would get if we used this regression approach, and we use this regression equation and use that to calculate our explained, error, and residual. So both these tables, the only difference is simply in the top table, I'm labeling it explained and error, and then in the bottom, I'm calling it between groups and within groups. So there's a little bit of a change in the terminology, but mathematically, these are the same tables, and we would get the exact same values to plug into this table, regardless of whether we're doing the regression approach or the group comparison approach. And the reason why it's all the same is because observed minus group mean, how far people deviate from their group means, is the same thing as how far people deviate from their predicted values. and the predicted values are the group means. And if we plug in this regression equation, it gives us predicted values, which are group means. So it all comes out the same regardless of how you do it. Now, many of the things I've been talking about work out best if you're coding or scoring the X variable as zeros and ones. If you have a treatment group as group 1, control group is group 0, then a lot of these things work out really nicely. But there are some things here that actually work out regardless of what values you use to code your X variable. So for example, here I've scored my X's rather than zeros and ones. I said, well, I'm going to call one group group 1 and one group group 2, so people get values of 1s and 2s. And actually what I'm showing you here is I have this data set where I have two groups. In this case, I call them group 1 and group 2, and they had scores on some outcome variable, and I plugged it into an analysis. And on the left, we see here each dot is someone's score. And so here's everyone's scores in group 1. And the mean for group 1 is right here. It looks like almost about right at a 30 or so. And then here we have everyone's score, all the dots over on the right-hand side of the people's scores in group 2. And the mean for group 2 looks like it's a little bit higher than 40. And so recall that if we're doing the group comparisons approach, each person's predicted score is simply their group mean. So if the mean for group 1 is right here, about 30 or so, then everyone in group 1, their predicted score is 30. And the mean for group 2 is right here, a little bit higher than 40. So everyone in group 2, their predicted score is right here at 40. Now, if I do plug this into a regression equation, where I say this outcome variable y, scored 0 to 70 or so, is predicted by scores on X, which in this case are now 1s and 2s. If I plug that into a regression equation, you get an intercept and a slope. That's what I've depicted on the right-hand side for this data set. So our intercept is right here. What is that, about 18 or so? And then here's our red lines, a slope. And note where the slope crosses right here at group 1, that gives a predicted score. So anyone who has a score of 1 on X, your predicted score is right at the slope right here. And note where that slope crosses. Our slope crosses the 1 right at the mean of group 1. And our slope goes up here and it crosses 2 on X. So if you have a score of 2 on X, where does it cross that value of 2 on X? It crosses right at the mean of 2. So note how both the left-hand side and the right figure, both these figures are showing the same thing. It's showing that if you're in group 1, your predicted value is right here, about almost 30. Same thing over here, right where that slope is. That slope crosses the value of 1 at almost 30. And if you're in group 2, your predicted score is up here, a little bit higher than 40. And so whether we think about it, your predicted score is your group mean, or if we were to actually do a regression equation and calculate a slope, get that equation where we have an intercept and a slope, and we calculate people's predicted scores, where we say your predicted score on y is equal to intercept plus slope times x, and your x score is your value for your group membership variable, we would get the exact same predicted scores either way. And as it turns out, we don't even need to have x's scored as zeros and ones in this case. It could actually be scored as any two values you pick. This will actually always be true. So regardless of how you score or how you code your x variable, the slope will always give the group mean as the predicted value. We've also talked about how if we take a correlation and square it, that gives us the percent of variance explained. And that will be true here as well. So if we think about this type of analysis from a regression approach, where we have scores on X, which is group membership, scored zeros and ones, and we're using X to predict Y, which says levels of happiness. And if we think about that in terms of just a simple regression equation, where we say predicted Y is equal to an intercept plus a slope times X, if I have just a simple regression equation where I have just one predictor, then my lowercase r squared would be the same thing as my uppercase r squared. That is, the lowercase r squared gives me the percent of variance explained by just one predictor, x, and the uppercase r squared gives me the percent of variance explained by all the predictors in my equation. But if I'm just doing a simple regression equation with just one predictor, then I just have one predictor. So either way, I'm looking at the same thing, the total percent of variance explained. And if we were to take that group comparisons approach we were just talking about in the previous video, and I noted that when we calculate the percent of variance explained from doing group comparisons, people usually call it eta squared rather than capital R squared. And I already mentioned that those two are the same thing. So if I'm looking at a situation where I have just two groups, I can put that in the framework of a simple regression equation where I'm using x to predict y, and x is group membership and y is the outcome variable. And we could calculate lowercase r squared, or it would be the same thing as uppercase r squared because it's just a simple regression equation at this point, which is the same thing as eta squared. In all cases, these are giving us the percent of variance explained. And in this situation where I have two groups and I want to see if there's a difference between these two groups in their mean levels on some outcome variable, there are many ways that I could do a significance test. There are many ways that I could do my inferential statistic to test the significance of the size of difference between two groups, which that effect size I might measure it with a D statistic talking about the size of difference between two groups. Or we could measure that effect size with a correlation, which is actually the correlation between x and y, where x is group membership and y is the outcome variable. Either way, there's several ways we could test the significance of this effect. So in our original unit, when we talked about doing simple contrast, I gave you this formula for a t-test, where we take the mean for group 1 minus the mean for group 2 divided by the standard error of the difference between two means. That is, a basic t-test is a statistic divided by its standard error. So if our statistic is the difference between two means, then we divide that by the standard error of the difference between the two means, and we get our t-value. Or we could think about this from a regression approach where we think about using x as our group membership variable and y as the outcome variable, and we're using x to predict y in a regression equation, and we get a beta weight. And which we saw in a moment ago, that beta weight is actually going to be the same thing as the size of difference between two groups. And if we divide that beta by the standard error of the beta, we will get a t-value for our beta weight. So that's another way we could do it. And then just in our previous video, we were talking about doing an F statistic, doing an F test using analysis of variance to test the significance of an omnibus effect. And we can actually apply this F statistic to this situation where I'm just comparing two groups. Now this is just a simple effect here. This would be a focused question where I'm just looking at a difference between two groups. But we could apply the F value here where we take our mean squared explained variance divided by mean square error to get an F statistic. And as it turns out, if I have just two groups, this is a special case of an F statistic. If I have just two groups in that situation, it turns out that your F will actually be the same thing as your t squared. And so with all these different approaches, this will actually give us the same answer no matter what. So your t-test, if you use this formula for the size of difference between means divided by the standard error difference between means, that will give you the exact same t-value if you use this formula, beta divided by the standard error of beta. You'll get the exact same t either way. And if you square that t, you will get the F statistic you would get if you do the ANOVA table and calculate mean squared explained divided by mean squared error. So these statistics are all related, and if you calculate a p-value, you will get the exact same p-value no matter what. So if you calculate the probability of this effect, if the null hypothesis is true, and if your p-value say it comes out to be 0.08 or maybe it's significant and it's 0.03. So if it's 0.03, it will be 0.03 if you use that formula. It will be 0.03 if you use this formula. It will be 0.03 if you use that formula. No matter which formula you use, you will get the exact same p-value. And I have a note up at the top here that this is actually true regardless of how you score x. So you could score x's zeros and ones, or you could pick any other, you could actually score x's. So maybe one group you're going to call this group 20, and the other group you'll call group 1042.64. You could pick any random two numbers and use that as your two coding values and score it that way. And these t-values, these significance tests will actually come out the same regardless of how you score things. And actually, I think I mentioned that on the previous slide as well, here that actually when I talked about the r squared being equal to the capital R squared being equal to eta squared, this is also something that is true regardless of how you score your X variables. So going back to that next slide again. So these, both your percent of variance explained and your significance tests, you will get the exact same values regardless of which formula you use of all the ones we've been looking at here, and actually regardless of how you score your X. As long as you pick any two values to do your coding with, it actually doesn't matter what two values you pick. And that covers a block of information that gives us a foundation for now going on to talk about how we actually do planned comparisons. One thing to note is that in that previous section, I've been talking a lot about how different statistics are measuring the same thing, how different statistics can actually give us the exact same numerical values. And if you keep that in mind, there will be some questions that I ask on homework assignments and on tests that will be very easy to answer if you keep in mind the fact that these different statistics can give us the exact same numerical values. And these questions on tests and homework will become very difficult to answer if you forget that fact. So, for example, maybe I say we're doing that, going back to that original idea of doing the simple contrast for comparing two groups, and I say, well, I do that simple contrast and I calculate my point by zero correlation, and say I do that and I get a value of, say, 0.3 for my point by zero correlation. And then I might ask a question. I say, so imagine what if I go and I do use a regression approach and I use X to predict Y and I calculate my standardized beta. What value do you think I'll get for that standardized beta? And if you recall, these are just two different ways of doing the exact same thing. It's a very easy question. Well, of course, that's going to be 0.3 as well. And if I say, well, what if I calculate my correlations taking the correlation divided by my product of two standard deviations? What will that be? Well, that will be the exact same thing. No matter how I do it, I'm going to get 0.3 either way. So if you recall that these formulas are all giving you the same answer, they're going to give you the same value, those questions become very easy to answer. And if you forget that they're all giving you the same value, then when I ask you these questions, they would be very difficult. So keep that in mind when you see questions on homework or on a test where I give you results from one analysis and then say, well, what if we use this analysis? What would we get there? That's just asking you to be aware of what statistics are going to give you identical values when you use them. And this completes everything for Part B of Unit 6.